In today's tutorial, we will have a look at the Baldwin rules. In the preceding tutorial, we were discussing the Baldwin classification of ring-closing reactions. As it turned out, empirically, it was found that certain reactions, certain ring-closing reactions, work very well, while others don't work at all. Well, what's going on? We will have a look. So with this starting material, an alcohol in the side chain and here an alpha-beta unsaturated ester, if we deprotonate just with a base -H+, we will have a nucleophile here, an alcoholate, and this alcoholate can attack at electrophilic centers, either this one, here we have a delta plus, beta to the carbonyl group, and of course at the carbonyl group itself. So if the alcoholate attacks that carbonyl group, then this five-membered ring is formed. And what kind of ring closing reaction is that according to the Baldwin classification? Well, five-membered ring formed, so we write down the 5. The bond which has been broken is the double bond. The double bond is transferred into a single bond, and the double bond was oriented outside that ring, and therefore we have to write down exo and not endo. And the reaction takes place at an sp2 hybridized center, so a trigonal center, and trig is the abbreviation we have to write down. So according to the Baldwin classification, this is a 5-exo trig ring closing reaction. So if this is protonated again, then this hemiacetal will fall apart, forming the carbonyl group, and this would be the final product of that reaction, a lactone, which is alpha-beta unsaturated. On the other hand, in principle, that alcoholate could also attack here. This would be a conjugate addition process, forming this again 5-membered ring, and here the ester enolate. So what kind of ring closing reaction would that be? So again 5, but now here the double bond is located within that forming 5-membered ring. The double bond is broken. So endo, but of course again sp2 hybridized trig. So this reaction has been tried. Those two reaction pathways are competing. After protonating, the protonation will take place here. This is the final product, and what was found is, well, nothing of this is formed, but 100% of that. Just an empirical finding, and that means this reaction, the 5-endo trig cyclization, does not work. At least not with period 2 elements like oxygen. With sulfur, it works at least a little bit. So what might be the reason? Well, for the nucleophilic attack, that oxygen has to approach in the trajectory for an anti-bonding molecular orbital here, and this does not fit very well. With sulfur, which is much bigger, it can then reach out to the right position, to the right trajectory. Okay, and this is Now the most important Baldwin rule. 5 endo-trig cyclizations generally do not work. Although just on paper or on the whiteboard it looks like just fine. It doesn't work. And this is not only the case for polar reactions, also for radical reactions. So this type of intermediate, a radical center here, could on that whiteboard give this 5-membered ring with a secondary radical here, but again, this would be also classified as a 5 endo-trig reaction. It doesn't work according to Baldwin. So, but with this kind of substrate, with one methylene group more than 6-membered rings would be formed. This here would be a 6 endo-trig cyclization. This is allowed according to Baldwin. And if that radical center does not attack here, but at that carbon, then this would be the next intermediate, and that ring closure reaction would be a 5 exotrig, which is also allowed. However, here we have a secondary radical, here a primary radical. Secondary radical is more stabilized, as we know. This would be preferred. But let's assume we have an additional methyl group here. Then also here would be a methyl group, and also there an additional methyl group. And then we would have in both cases secondary radicals formed, and in this case indeed we have a real competition between the 6 endo-trig reaction and the 5 exotrig reaction. Thanks for listening.